one where you, the one that was there, I moved it where the markers are.
Going to look today at some diffusion effects. We'll start with diffusion, and then we will move on to a couple of related things. And what diffusion is, oh, I was expecting there to be a bottle inside this pouch. It's not, it's just a pouch. What diffusion is movement of particles away from areas where they are in high concentration and into areas where they're in low concentration. And we've all seen this. It's not anything that's new and mysterious to us. And the explanation of why it happens is, simple. So let's do an example. Okay, I have a beaker. And I just about filled it with water. There it is. And I'm going to add some copper sulfate. Copper is a transition metal, and the transition metals show themselves, their chemistry, different from the other metals in that they have variable oxidation states and that they're very oftentimes colored. And an individual metal is allowed to have multiple different colors depending on what you attach it to and what their oxidation states are. So something like chromium, which is called chromium because it literally means color, can have multiple different colors across what you're looking at. So this is copper sulfate. It is this recognizably blue thing. These are very fine crystals. I was actually hoping for bigger chunks than this, but it'll do. And copper sulfate should be relatively soluble in water. What will happen, I'll put this in the copper. What will happen is that will fall to the bottom of the flask because it's a solid, and solids are more dense than liquids. And then over the course of some time, even if I don't pick this up and swirl it, over the course of time, the area where the copper is in high concentration is currently at the bottom of the flask. And the top of the flask, well, the top of the flask is just colorless. Over time, this will dissolve, and it will dissolve to uniformity, that every place inside this beaker will be the same color. And one place won't be darker than the other, and there'll be no sediment left. It will dissolve, and it will dissolve completely, which is the key to how all of this works. If this is the material that I'm looking at, there you go, and I will color those particles in. Right now, they are in high concentration. Well, what else is in the beaker? What else is in the beaker is millions and millions and millions and millions and millions of something else. Something else. For us, it's solvent molecules, but for gases, because we're still in the chapter about gases, diffusion works equally well for solutions or mixtures of gases. I'm going to have to draw a smaller beaker. When you realize that this could be a mixture of gases, that here is the first gas, and then here's the other gas, or here is the solute, and then here is the solvent, we're going to make a solution, and ultimately we're going to get to a situation where we get an equal distribution. I've made my particles bigger as a bit of a cheat. You end up with an equal distribution. Why? Let's see if we can get to why. What's the driving force here? This is something we've seen before, we've mentioned it before, but we haven't mentioned it in these terms. And it's one of the things that underlies lots of the physical behavior that we see in the world that we kind of had previously assumed, well, there's something mysterious going on. That's the invisible hand making these things happen. Could be simpler than that. Could be simpler. With all of the particles clustered together versus the particles separated, in terms of probability, it's probability again. Which one of these two scenarios is the most likely? This one. Because all of these are interchangeable. They're all interchangeable. This has less chances of occurring than that. Now, I know that the last time we said it, it kind of sounded like it was the opposite, but it was a slightly different scenario. This is less than that. And we have a little thing that helps when you're in doubt. This is ordered, and this is disordered. And a measurement of order or disorder in the universe is called entropy. If you stick around for chemistry 2, we're going to quantify entropy. It's given symbol S, and we talk about its values. Its values are usually small, much, much smaller than enthalpy, which is, an actual physically measurable change in energy. Here, entropy is low, and here, entropy is high. The amount of disorder is high. Which one does the universe want? Does the universe reward you for low entropy or for high entropy? High entropy. The tornadoes never ever blow through a brickyard, pick up the bricks and put them down in the shape of a house. Never, ever, ever. They do, however, blow through towns and turn the houses into piles of bricks. Nature is always heading for higher entropy. It's one of the laws of thermodynamics that the entropy of the entire universe is continuously increasing. And anything that you do that orders things has to have some sort of external energy to keep it that way. When you let nature at things, it just jumbles everything up. So this jumbled up answer is more likely than this localized answer. And so we see that it hasn't happened yet. I didn't test it before we started. We'll see how long it takes. Little convection currents going on in here. So whatever is dissolving is ever so slowly coming into solution and then moving away. It's going to take a while. Of course, I could pick it up and swirl it. And when I pick it up and swirl it, what I do is I do the universe's job for it. Is I just do this. And I move things around. And I take the particles that were on the surface that had already dissolved but hadn't gone very far, and then I relocate them somewhere else. So that's why agitation makes things dissolve faster. Mixing helps gases and liquids mix faster. Okay, that's diffusion. And it's true of solutions, and it's true of gases. There's, natural gas that gets piped into your house. It doesn't really have much of a smell. So we add a smell agent into the gas called thiophene. Thiophene's got a sulfur in it, and sulfur smells like rotten eggs. And so when there's a gas leak in your neighborhood, you can smell it. You can be walking your dog down the street and know, hold on a minute, I can smell that. I can smell the gas leak. What you're smelling is the added chemical that they've put in. Well, this is a diffusion effect of, there's a gas leak, but it's way over there. But that gas has come into the room, and now the universe is just mixing all of those chemicals together, because when it comes out of the pipe over there, it's in high concentration. And the universe doesn't want that. It wants it all to be mixed up. It wants more disorder. So the air currents and everything else and the diffusion effect wafts those gases around to the point where we smell the gas and call the gas board. And they come out and fix the pipe. There's an adaptation of this, and it's called effusion. And what effusion is this. Okay. If I had a container and that container contained two materials. We're going to have these be gases, but they could be solutions. They could even be solids, as long as those solids are movable. So there's an example that we can do with colored balls in a box. There's a partition here. So if I've got like little golf ball size balls in a box, and these ones are blue and those ones are white, and there's a piece of cardboard separating those two worlds, then I can pick that box up and move it around, and they stay where they are. When I take the partition out and shake it, well, we all know what we're going to get. We're going to get that to be disordered. And if I say, keep shaking it until it goes back to all the blue being on one side and all the white being on the other side, you're going to shake forever, because it's never, ever going to happen again. This is entropy. And all that entropy is what's more likely? There are more mathematical permutations for everything to be mixed up than there are for them to be ordered like this. Okay. The adaptation for effusion is that these are actually two separate containers with a pinhole, with a hole or a tube. So we just moved slightly out of the realm of just pure science and into the realm of engineering. Engineers really need to know this kind of information. Is that if I've got a gas and it's in this container and I need to get it into that container, how long is it going to take me for that gas to flow down this pipe? Okay. Effusion is diffusion, but through a hole. So it's limited. There's a limit. It's not just a free-for-all. Everything has to go through this hole. And this is subject to a rule. It's called Graham's law. And Graham's law of effusion tells us that if I have to get particles through a hole, then the rate at which they go through that hole has to be proportional to the speed at which they are moving themselves. This is something that we've hinted at before. If the blue gases are hydrogens and the white gases are chlorines, and we're all at the same temperature, so we all have the same average kinetic energy, which one of these gases is moving the fastest? The hydrogen is, because it has the lower mass. We have to think about momentum. Momentum is mass times velocity, mass times speed, right? Which ties into the energy. So if you have something that is small and light, you can pick it up and throw it far. If you've got something that's big and heavy, you cannot pick it up and throw it nearly as far. So the light gases are moving faster than the heavy gases, which means the light gases, they're the ones that are going to be going through the hole most frequently. And when these two things have to mix, it's going to be the light gases that are responsible for that, because they're the ones that are going to get through the hole first. Graham's law of diffusion is written two ways. It can either be written in terms of time, or it can be written in terms of rate. What exactly is a rate? If a question on the test was, give me an example of a rate and define what a rate is. What is a rate? It is something per something.
Like, I guess you could have, like,
Yeah, it could be meters per second. Meters per second is an example of a rate. Is grams per milliliter, that's something divided by something. Is grams per milliliter an example of a rate? No. Why not?
because we're talking about mass.
Okay, what about meters per, grams per second? If I had a hole and I wanted to measure how many grams of this liquid fell out of the container every second, and I measured that grams per second, would that be a rate? Yes, it would. So what makes a rate be a rate? It's to do with time. It is something divided by time. So when you see Graham's law of diffusion, it can either be written as time or it can be written as a rate. Rates are the inverse of time. Time's going to be in seconds. Rates are going to be in something per second. So when you see Graham's law of diffusion, it can either be written this way or that way. Okay, so I'm going to look in the book and see which one it gives us. And from there, I'm going to show you the other one. So our book has Graham's law of diffusion on page 424, and it does this by rate. Okay, so I'll write it the way that the book says it first, and then we'll just use logic and fix it. It says if I have two gases, the rate of the first one divided by the rate of the second one. I'm not going to use numbers. I'm going to call these A and B. I think our book uses 1 and 2. Yeah, let's not use 1 and 2 because that feels like it's a number. The rate of A divided by the rate of B. Let's have this one be A and that one be B. There you go. The rate at which A flows through that tube divided by the rate at which B floats through that tube is equal to the square root of the formula mass of B divided by the formula mass of A. Whatever this rate is and whatever that rate is, they're going to be in the same units. So these units are going to cancel out, and that formula mass is in grams per mole, and this is in grams per mole, so that cancels out. Well, this is a ratio to another ratio. This is dimensionless. There's no units for this. Okay? So if the ratio of rate to rate, and remember that a rate is something over time. Rate and time have an inverse relationship. If you're going very, very fast, it takes you a short amount of time to get there. If you're going very, very slow, it takes you a long time to get to your destination. Rate and time are the inverse of each other, which means if I wanted to talk about this in terms of time, this is a direct relationship. This is an inverse relationship, okay? And these questions can come to you either way. It can either be written as a time or it can be written as a rate. We could say it takes this amount of time for the gas to get through the hole. Or it could say we sat and clocked the number of particles passing through the hole every second, and in a second, I've got this many particles passing through. So it can be given to you as a rate or as a time. Okay. Are my glasses on my head? No, they're over here. All right. We can do the example that's in the book. Book has an example. It says an unknown gas composed of a homonuclear diatomic molecule diffuses at a rate that is only 0.355 times that of oxygen at the same temperature. Calculate the molar mass of the unknown. Oh, here's another thing. Because this is a ratio to a ratio, your question might not even come with numbers. It might not even come with actual physical data. It might say, this one takes twice as long as that one. So you make this one be equal to 1 period of time, and therefore this is 2 periods of time, and it's just 2 divided by 1. It could say, this one is 4 times faster than that. So you just put a 4 here and a 1 there. Okay? Let's do the one that's in the book. Where's my eraser? We get to use the square root button on your calculator today. Question. There's a gas. and it diffuses through a pinhole at 0.355 times the rate that oxygen does. Identify the gas. Okay. Question says, this is a rate. If it said anything in the question like grams per second or moles per minute or anything that was a unit of time divided by a unit of time, you would know it's a rate. If it says it took this amount of time, you would know it was a time. This one says it's a rate. So that's the version of Graham's law that we're going to use. This unknown homonuclear diatomic, two atoms of the same type stuck together. There is no X on the periodic table. X is a placeholder. We're going to find out what the value of X is. So our unknown diatomic molecule is X2, and it diffuses through a pinhole at this times the rate for oxygen, and we know that oxygen is O2. Okay? So Graham's law tells me that the rate of X2, let me see if it matters. It doesn't matter which one you put on the top and which one you put on the bottom. I'm just going to use the same numbers that it says in the book. The rate that it takes X2 to go through the hole divided by the rate that it takes O2 to go through the hole is equal to the square root of the formula mass of O2 divided by the formula mass of X2. All right. Can you see that this number's in the question? That number's in the question, but it hasn't been explicitly stated. What are we going to make this number be? 1. Because this is a ratio of 0.355 to 1. But that is 1/3 as fast as this. Okay, so we're going to put a 0.35 here and a 1 there. The formula mass of oxygen, I could find out on the periodic table. So the thing that we're going to solve for is the formula mass of our unknown. And then if we divide that in half, we'll know what the atomic mass of X is. And then we can go look on the periodic table and find what the identity of this unknown atom is. Okay? Have a stab at it. Have a stab at it. Put the numbers in the places where they belong. I don't know if you can see this, and you probably can't see it on camera, but right now, this much of the top of this solution is still colorless. This much of it is a very faint blue. It's starting to mix. Ultimately, it's all going to be the same color. I just spilled somewhere. Agitation helps. When I repeat this at 1 o'clock, I'm going to make the water be hot. I'm going to go to the tap and get some hot water. It's going to make it work faster. Have a stab at this calculation. Let's see how far you can get. And you are all responsible for knowing where this, the square root button on your calculator of choice is. The other numbers have so many digits of precision, it doesn't seem right to just say that an oxygen is 16. If you just put the numbers into the calculation, you get this far. The 0.35 divided by 1, which is 0.35, is equal to the square root of 32 divided by whatever the formula mass of x is. Okay. At this point, I'm stuck because I don't know what a square root is, and I don't know how to get rid of it, which means I can't find my final answer. If there's a square root in your equation, how do you make it go away? So the square root is the thing that when you square it gives you the number. So, you know, the square root of 4 is 2, because 2 times 2 is 4. So to make the square root go away, you square it. You times it by itself. So I'm going to times multiply this entire equation by itself. And when I times, so 2 is the square root of 4. So if this was the square root of 4, and I times it by itself, I would just get 4, because square root of 4 is 2. 2 times 2 is 4. I'm going to multiply everything in this equation by itself, both sides. And when I multiply 32 over x2 root by the root of 32 over x2, I get this. And when I multiply the right-hand side, left-hand side, I get that. I've squared both sides. Multiply both sides by themselves. Makes the square root go away. So we didn't even get to use the square root button. We didn't have to, just use logic. Sometimes you do, sometimes you don't. Okay. What is 0.355 squared? What number goes here?
Okay. 126.
Okay. So 0.126 is equal to 32 divided by the formula mass of x2. All right. Algebra. This number is equal to that number divided by that number. A is equal to B divided by C. This number is equal to that number divided by that number. This number is equal to that number divided by that number. The number I want is C. That's the value that I want to find. If A equals B divided by C, what does C equal? We have a difference of opinion. Write it down. I'll ask you again in a minute. Every time you move a term across the equal sign, it changes. If it's a numerator, it becomes a denominator. If it was a denominator, it becomes a numerator. Write it down and let's see if we can figure it out. If A equals B divided by C, what does C equal?
A divided by
A divided by B.
B. B divided by
Okay. So I now have two answers instead of three. Are you still going to stick with your A times B? Okay, let's figure it out. I'm going to move the C. It's a denominator. I don't want it to be a denominator. I need it to be a numerator. I need it to be above the line. So I'm going to move it across the equal sign where it goes up here. So I have just changed this equation. This equation now says C times A equals B. At this point, I need to remove where the A is. I need to get it out of the way. So I'm going to push it across the equal sign where it becomes a denominator. C equals B divided by A. If C equals B divided by A, and over here it was A, B, C, then what this means is that the formula mass of X2 is 31.999 divided by 0.126. Formula mass of X2 equals what?
253.
The formula mass of two atoms that are the same as each other stuck together is 254. Therefore, the formula mass of X, or really atomic mass of X, is 254 divided by 2, which is what? 127.
126.98.
So what's the identity of X? Mm-hmm. And what's that called?
Oh.
The other vapor, gas, is iodine. Oh, that reminds me. I have some iodine in my office. Iodine does something very, very strange. We'll do it on Friday. It goes directly from being a solid to being a gas. It does not go through the liquid phase. It does something called sublimation. Turns directly from a solid to being a gas. All right, I'll see you Friday.